Okay, let's look at this problem. So two long wires, one of which has a semicircular bend of radius r, are positioned as shown in the accompanying figure. If both wires carry a current I, how far apart must their parallel section be so that the net magnetic field at P is zero? Does the current in the straight wire flow up or down? Okay, so the two equations we'll use is, again, we're using Biot-Savart's law. The magnetic field produced by an element of current I ds is element of current ds carrying a current I, element wire carrying a current I is given by this. And from this expression you can see that, and using the right hand rule for direction of the cross product, this straight section will not produce a magnetic field there. This straight section will not produce a magnetic field at that point. Okay, and use your right hand rule. This element of current, if you stick your thumb of your right hand along there, and your fingers will give you the direction of the field at this point. This element will produce a field into the sheet. B will be into the sheet at that point. Okay. Now, in the problem, what we want is, we want the field at this point to be zero. So this wire has to produce a field coming out of the plane. So, and if the current is flowing in this wire is in that direction, that will produce a magnetic field coming out of the sheet. So that's what we want. Okay, so for the two fields to cancel, so the current in this wire is in the upward direction, and we'll figure out the magnitude. The strength of that, the magnitude of that magnetic field is given by mu naught I by 2 pi a. Okay, a is the distance between that. Okay, all right, so now let's calculate the magnetic field due to the curved section at P. B, let me write this, B due to the semicircular current due to the half circle at P. And that's just all those little elements, as we said, are pointing into the sheet. So all we need to do is add up all those magnetic fields. Okay, and we're adding up mu naught I by 4 pi ds, and they're all at a distance of a. No, not a. What is the radius? R. Okay, so this is all constant, mu naught I 4 pi r squared, and the length of that half circle is pi r. So this magnetic field is, the pi cancels, one of the r cancels, is mu naught I by 4r. Okay, so now in a couple of problems now we have found that the field at the center of the circle produced by a semicircle is mu naught I by 4r. All right, let's add another sheet first before we finish the problem. Okay, now the field at P due to the straight section. So there is P, the field at P due to this straight section is using your right hand rule, you point your thumb along there, and the field will come out of the sheet. So the field is coming out of the sheet, and this field, we'll call it this field due to the straight section, is mu naught I over 2 pi A. All right, and what we want is the net field to be 0. Net field to be 0, so the field due to the semicircle is, we'll call that positive, which is going into the sheet, and we'll call the straight one negative. Okay. You want this to be 0. All right, so okay, so what we want is mu naught I for R equal mu naught I 2 pi A. So A, of course, this all this cancels. This is 2. So A is equal to 2R. A is 2 by pi R. So that's how far the wire needs to be for the net field to be 0 at that point. Okay, let's see, does that cover that problem? Yep. Okay, that ends that.